standard deviation of a binomially distributed random variable. Now I believe in Triola's 5th edition here, this is just a totally new section. I think he's put this into the last section, and I think he did that in edition 4 as well, if I remember correctly. So we'd actually be in section 5.4, I think, at this point in time. So just note that in Triola's 4th and 5th editions, I believe this is now titled section 5.4, and I think in edition 5 he says that these are titled the parameters of the binomial distribution. I think that is the title of this section. So titled binomial distributions parameters. All right, so just to keep it kind of straight here. So the mean of a binomially distributed random variable, note that we do use the population notations here because these aren't from relative frequency probabilities that we're getting these P's. These are from classic probabilities, and so this is giving us our population. And Triola also has a nice little explanation of that in his book this time around. And to get the mean, you multiply the n times the p, and that's all there is to it. Now to get the variance, because we always have to start with variance, that's n times p times q. Now notice n times p is just the mean, so this is the mean times the q. That's another way of thinking about that. And then if we want the standard deviation, sigma, we're going to take the square root of the variance, n times p times q. And usually it, of course, is that we're going to be wanting the standard deviation, not the variance, because these have squared units in variance, right? And squared units are not very useful to us, so we're not real fond of the variance. We want the standard deviations, which are a little bit easier to interpret, but you can't get the standard deviation except for going through the variance as usual. All right, so now going here to this next example, it says, so back in our underprepared student in the last example, what would you expect the student to get on the test? So this question is expected value, and expected value, right, is nothing more than the mean. So expected value of x, that's nothing more than the mean, which is equal to n, which is 10 questions, times the probability of success, 1 out of 5. And so that means on average, you would expect the student to get 2 questions correct if they were flat out guessing on the test. That's not a very good a good grade, is it? 2 out of 10, that's going to give you a 20%, and 20% is definitely failing. All right, now looking at the next one, this word Triola was really fond of in all of his editions up until edition 4, and that was consistently. And consistently was used in order to say one standard deviation. So what range would you expect the student to be within one standard deviation? And I'm just going to write it that way. And in 5th edition, he's not using that word consistently. He's really just going for the next one with the unusuals and the unlikelies. And he's redefined for edition 5 this unusual and unlikely, and they link closely together, but he uses a little bit of different terminology, but they're linking to the 2 standard deviations. So consistently here, this is the 1 standard deviation. So consistently, the range that you would be looking at for 1 standard deviation, of course we need to find the standard deviation. So the standard deviation is the 10 times the 1/5 and then times the 4/5. So the this ends up being the square root of, this was 2, and then 2 times 4/5 would be 8/5, and then we have to take the square root of that value, and the square root of 8 divided by 5, and that gives us 1.264911, and that's approximately, right? And then 1 decimal point, 1.3 here. So that's our standard deviation. So consistently would be our mean 2 plus or minus this 1.3. And so this would be 2 plus this to 2 minus this. So in the range of 2 minus 1.3, which is 0.7, and I'm using interval notation to note this, of a range of 0.7 to 3.5. So remember from algebra, your interval notations, right, that say that these are the range of values. So thinking about this on a number line, what we have going on here is here's your mean 2, and then here is 1, and here is 0, and then here's 3, and then here's 4. So if this is your range, then we would expect it to go down to somewhere in that range there, up to, and then 3.3 somewhere in that range there. So it's a symmetric interval about the mean here. And that's just what this interval notation tells you about. Now, the next question says, what would you say would be unusually high? Well, unusual is telling you that you want something outside the 2 standard deviations. So above 2 standard deviation point. So what we have to do is we have to find that computation for 2 standard deviations. So the mean 2 plus, because it's above, right, high, so above 2 times the standard deviation of 1.3, and so this is 2 plus 2.6 or 4.6. So what we're looking at here is on the number line, right, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So here are all of our possible number of correct problems, right? Here's your average right in here, right? So this is your mean. And then here's your 4. And then here's 4.5, so 4.6 being somewhere like right in here. If you get anywhere in this range here, this would be considered unusual because it's outside the 2 standard deviations. So if we got above a 4.6, we would be expecting that to be somewhat unusual. That's still an F, right? I mean, you're still getting an F, but you're getting a high F. Now, it's also interesting to note here that we're giving values that are decimals, and we know these are discrete values. But remember, when we use our parameters, we're not expecting to get values that we could actually get out of the data set. We're expecting to get things that tell us it's kind of right around there, maybe a little bit higher than this, but a little bit lower than that. They're giving us an idea of where these would lie in the actual population. All right, so now let's move on to our next problem here, which is just to use the same sort of thing to find for a different binomially distributed random variable, just giving you another opportunity to look at the binomial distribution. So one last example, coming back to our expected value. A company produced widgets in very large lots. Very large lots, that's telling us sampling without replacement is still going to give us independent trials, and with a defective rate of 10% per lot. Well, defective rates, it's either defective or it's not defective. There's your 2 possible outcomes. And for a particular sale, a batch of 4 items is going to be chosen. So we're going to choose batches of 4. That's our number of trials is 4. And we want to find the expected repair cost for a single widget. And so we have our N, which is equal to 4. Our probability of finding a defective, which is 0.1, which then leads to our Q, which is 1 minus 0.1, which would be 0.9. And then we have our expected value. So expected value here is our N times P, so 4 times 0.1. So an expected value is the average number of defectives in a lot, so that's our mean. That's 0.4. Now, if we expect 0.4 to be defective and our cost is 15, we're going to multiply the $15 times the 0.4, and that's going to give us our expected cost for repair. So 15 times 0.4 is going to give us $6. So where this comes in real business world, is this is the amount that would be a fair cost to charge for a warranty. So this is the expected repair costs on those widgets. And again, that would be the amount that would be a fair price to charge if you were going to charge somebody for having a some kind of a warranty. And of course, they're going to charge more because they want to make money on their warranties. So they might charge a $10 warranty cost on this on these widgets, and then they would be making a profit of $4 every time. So their expected profit would be 4 times 0.4, or 4 times $1.60, right? They expect a profit of $1.60 for every widget that they sold a warranty on. So that would be kind of an interesting thing to think about too. There'd be a little bit more difficulty in computing that probability, just because not every widget sold would probably come with a warranty. So they'd probably figure that in and help to decide how much more should they be charging based upon the expected cost of repair being $6. All right, and that wraps up Chapter 5.